Okay, so welcome back everyone. Welcome to this live problem solving session of the course Essentials of Topology. So this course is instructed by Professor S.P. Tiwari from IIT ISM Dhanbad, and I am Siddhartha Pramanik. I am a PhD student at the Department of Mathematics, IIT Kharagpur. So this live session is for the week 4. So if you guys have any doubts from the lectures till now, so you can feel free to ask your doubt. So I got one question from you people, that you people are having confusion between the box topology and product topology. So if you have seen the lectures, so I will just clear the doubts first, then I will come to those problems which I have picked for you, so that it will help you to solve some uh, assignment problems. So first let's see the box topology and product topology. Okay, even before that I will just quickly summarize the topics. So in this week, we have started with creating many topologies from known topologies, and among them, the first one is subspace topology. And in subspace topology, we have seen how to define this topology, what will be the open sets, what will be the closed sets, and how to define a basis of the subspace topology from the basis of the original topology, and how the neighborhoods and some other things looks like in the subspace topology. And after that we have defined product topology in Cartesian product of sets. And even we have defined one more topology in the Cartesian product of sets, which is box topology. And the other thing is the using a surjective function, we have defined a topology on the codomain known as the quotient topology. And in the final lecture of this week, we have seen one special type of set function, which is known as Kuratowski closure operator, or interior operator. And using this, we have defined topologies on a set. So these are the overall main topics of this week. So one of your doubts is how the box topology and the product topology are different. So first thing is uh, okay. So let you just take a indexed family of topological spaces. So here xi comma tau I, these are topological spaces, and you have And you have a family of topological spaces where I is an indexed set. So uh, in particular, you can consider this Cartesian product, right? So in this Cartesian product, using these known topologies, how you can define a topology? That is the main point. So there are two natural ways to define, to do this thing. So one is the product topology and one is the box topology. And one important thing is, if your index set is finite, then there is no difference between box topology and product topology. This difference will occur when your index set is infinite. So how they are different, that will be clear from the definition itself. So how this product topology is defined, can anyone recall? Yes, what will be the definition of this product topology? Anyone?
For the product topology, it will be the xi will be equal to gi for all I that is not greater, not finite, and then for finite it will be xi.
Okay, so this product topology is actually so what will be the natural basis? So if you see, the basis is basically product of all gi where I belongs to I, such that gi belongs to tau I for all I belongs to I, and gi is not equals to xi for all but finitely many I. So what does it mean? So you are taking product of these open sets. It is like G1 cross G2 and so on. But these GIs are open sets in tau I. But you can only take finitely many proper subset, proper GI. Right. So you can take only like G1 cross X2 cross X3 and so on. So only finitely many, in the finitely many coordinate you will have only proper subsets, and all other coordinates will be the whole set. So that is the basis for the product topology. But for box topology, what we do is, uh, we avoid the second condition. We just remove the second condition. We can take any product of open sets. So this box topology is generated by, you take just product of these open sets where gi belongs to tau I for all I belongs to I. That's all. There is no restriction on gi. So you can clearly see that this collection is bigger than this collection. And even if your index set I is infinite, this type of elements may not be in the product topology. That's why the product topology is smaller or coarser than the box topology. And you will see in terms of projection functions and continuous functions maybe in the next week. Uh, there is one more definition for product topology in terms of those projection functions. So I think till now these definitions you can remember, and in the next week you will see some more results on these topologies. Then I think you will have more clear concepts in this topic.
Sir, for the product topology, GI is equal to Xi or not equal to Xi? Means I'm getting little bit confused. GI equal to Xi for infinitely many,
Yes,
except but what we have written in the definition, GI is not equal to Xi
yes,
for all, but finitely many.
yeah.
GI is
So
not equal to Xi.
the meaning is GI is proper subset of Xi only for finitely many I. Okay, so that is the terminology. So this means GI is a proper subset of Xi for only finitely many index I. Okay, so that is the meaning.
Okay, sir.
Yeah, so that is the usual terminology. Okay, any other doubts or queries so far? Okay, maybe we will do some more problems on this product and box topologies, then it will be more clear for you today. So remember one thing, that if your index set is finite, then there is no difference between box topology and product topology. All are same. Okay, so if there is no other doubts, so let's solve some problems. And these problems will help you to do the assignment problems also. So try to focus on this. So in the subspace topology, we know how the open sets, closed sets, and some other things looks like. Uh, but okay, so let y comma tau y be a subspace of x comma tau. Okay, and let a is subset of y. So a is a is subset of y and also a is subset of x, right? So we have two topologies. So one thing, you can consider the closure of a in x comma tau, as well as you can consider this closure in y comma tau y. So what will be the relation? So how to compute this? So for, okay, so maybe I will write. So to distinguish the notation, I will just write closure of a in y. Okay, in y means in the topological space y comma tau y. So then this set will be equals to closure of a in x and you intersect with y. So this question is saying, if you want to compute the closure of a in this subspace topology, what you have to do is you just compute the closure in the bigger topology and you intersect with your subspace. That's all. So this is one thing. The second is okay, how to write. So similarly, you can consider the derived sets. So if you take the derived set or the set of all limit points in y, okay, so I am using this notation this to just distinguish between the topological spaces. this will be equals to the limit points of a in x and you intersect with y. Okay, and the third thing is the other thing is boundary, how the boundary will look like. So if you see the boundary of a in x, it will be subset of boundary in y. Sorry, the other way. So boundary in y will be subset of boundary in x intersect with y. And the last thing is the interior. So interior of a in y will contain interior of a in x intersect with y. So we have to prove these four things. Okay, so we have to prove these four relations. So I hope the question is clear. Okay, and also maybe I will write here, give example where equality will not hold. Okay, for both. Give examples where equality may not hold. Okay, so I hope the question is clear. Okay, so let's try to prove the first one. So I will not do all the thing. So these are just routine check. I will just do the few things so that it will help you to do the computations in some particular cases, because you might see some related problems in the assignments. So let's start with the first one. So we have to prove this equality. Closure of a in y is same as closure of a in x intersection with y. So how to do this? So we have to prove both side inequality. So one thing, a is subset of y, that is given, and a is subset of the closure, right? That also we know. So if we combine this, then you will get a is subset of closure of a in x intersection y. But what about this set? This is a closed set in y, right? So this one is a closed set in x and you are intersecting with your subspace. So this is a closed set in y. So this is closed in y comma tau y. So this closed set contain a, but closure of a in y is the smallest closed set which contains a. So this implies closure of a in y should be subset of this, because this is the smallest closed set in y which contains a. Closed set in y comma tau y containing a. So this gives one inclusion. So we got this side inclusion. We need to prove the other inclusion. Okay, so now closure of A in Y is a closed set in Y comma tau Y. But this is the subspace topology. So how the closed sets looks like? So this closure of A in Y must be looks like some closed set in X intersection with Y. So where A is a closed set. So this thing we have already seen in the lectures. So this implies your A is subset of this closure and this is subset of F intersection Y. And this is subset of F. So that means A is subset of F and F is a closed set in X. So what can we say from here? So closure of A in X should be subset of F because this is the smallest closed set in X which contains A. So now F contains closure of this and also F contains closure of A in X. So what can you say from here? So you can see that then closure of X in A, if you intersect it with Y, this is subset of closure of A in X and this is subset of F. Okay, maybe the other thing. So this is subset of F intersection Y, right? And but what is this? This is your closure of A in Y. So this gives the other inclusion. Yes, any doubts? Okay, so we have got both inclusion. So this proves the first result. So now what about the second one? Maybe I will leave this second and third one to you and I will prove the fourth one because these are just routine checks, but if you know these results then it will help you to do some other problems. So B and C are exercise for you. You can try this. Let's do the interior part. So what we have to prove is interior of A in Y contains interior of A in X intersection Y. So let me write it here. This will contain interior of A in X intersection Y. Okay, so this is also easy. So can you see why this is true?
Sir, because y is a subset of x, and the basis elements of y would be containing would be x. Y intersection open sets in x,
Yes.
so the interior would be inside.
Uh, no, actually, from your reason, it is not clear this inclusion. So can you see it in some other way? So so we already know that interior of a set is always contained in the set, right? And this is subset of Y. So what you can see is uh, interior of A in X, and if you intersect with Y, this should be subset of A. But this is a open set in X, and you are intersecting it with Y. So this whole intersection is an open set in Y. This, okay, maybe I will just write this thing belongs to tau Y. And what we know about interior? What is the definition? It is the largest open set contained in that set. So this is an open set contained in A. So this should be contained in the largest open set contained in A, which is the interior of A in Y. Because interior of A in Y is the largest open set contained in A with respect to tau Y. So the proof is very easy actually, and we need to give an example where the equality will not hold. Yeah, do you have any example in your mind? This is very easy actually.
If you take if you take the set x as r
Sorry, can you
and
be a
y
little bit
as
louder?
q. Sir, if we take the set x as r and if we take the set y as q rationals,
Okay,
then
and what will be your A?
then the interior of q is empty set. Interior of r is
So
the
interior of Q is empty in both uh, subspace topology and in the original topology. So equality will hold in that case. So you are in the right direction, but you need to take some other thing. So let's take X is R with the usual topology, and let's take Y as closed 0 open 1, and let's take your A as closed 0 open half. Then what will be your interior of A in X? Can you see? Can you say? This
open
is,
interval 0 to 1
yes,
half.
exactly. But what will be your interior of A in Y?
Interior A itself.
Yeah, it is A itself. So your interior of A in Y, this properly contains your interior of A in X intersection Y, which is open interval. Okay, maybe you can take similar type of examples for the boundary also. So I will not go into that, but keep these results in mind. It will help you to compute these closures and all other derived sets. Okay, so any doubts so far? Yes. Do you have any doubt? Your voice is not coming actually. Maybe try writing in the chat box. Yeah, do you have any doubts or what?
Sir, hello.
Yes. Yes.
Sir, I am saying that in case of Euclidean topology, the equality always hold for C and D.
For C
What
and
are the conditions under which the equality holds?
that we need to check because in these examples we are also taking the Euclidean topology, right? But the equality is not holding.
Yes, sir.
Yes. So maybe if your subspace is open,
If
then
subspace, yes, sir. If subspace
then
open,
then might be D is
D.
then maybe D you get equality.
And in case of C, if Y is closed, then I
Maybe
think,
I am not sure, but it may be the case.
oh, yes, sir.
Yeah, maybe you can try to prove this. Maybe just try it. Let me know also if this holds. Okay, and any other doubts? Okay, so if we have no other doubts, let's move on. So for the product topology also, I will give you similar type of results. But before that, let's do an interesting problem on the product. Uh, this is question number 2. So this is from GATE 2018. So we have to compare the topologies. So let uh, x uh, let x equals to R2 with the Euclidean topology or usual topology, and let y equals to R with the cofinite topology. Okay, and let z is the product topology y cross y with the product topology. Okay, then which one is true? The first one is the topology on X is same as the topology of Z. is same as the topology on Z, B is the topology on X is strictly coarser than the topology on Z. The fourth one is the other way. So I will just copy it. So topology on Z is strictly coarser than the topology on X, and the option D is the topologies are incomparable. The topology on X cannot be compared with the topology on Z. So we have four options. So let's try to understand the question. Here X is the R2, the Euclidean plane, and with the Euclidean topology. X is R2 comma tau E, and Y is R with the cofinite topology, and Z is the product of R with itself and with the product topology. So here we are taking tau cofinite topology cross tau cofinite topology. Now we have to compare between X and Z. So this is very easy actually. You just have to use the definition. So do you have any answer for this? Or can you see which one will be true?
Not comparable.
So these are not comparable. Why?
Yes, sir, because cofinite and Euclidean are not comparable in if you take R.
So you are saying R with tau E and R with cofinite topology, these two are not comparable?
Yes, sir.
No, this is not true. And actually, the cofinite topology is strictly smaller than the Euclidean topology. So this thing has been done in the lectures, or you can just go back to the lectures and you can check this.
So the open sets we can take here, it will be either R is the only open set, and one more thing is R minus finite set, since its complement should be finite.
Yes.
So in that reason, if we are going to check means, then it will be coarser, means the topology in Z is coarser than the topology on X.
So yes, it is coarser, but the
Means
options are
when
strictly coarser or not.
means topology on Z is strictly coarser than the topology on X. Since X the topology X is entire R2.
The topology on X is the Euclidean topology, and
So it will generate entire R2, and whereas the topology R into R means if I am going to take the open sets in the format R minus X1 like that, whose complement is finite, then
no,
some elements are
your
left out.
first reason is correct. It will be coarser, but why it will be strictly coarser? Can you give any specific example? So first note that R with tau cofinite topology is strictly coarser than R with the Euclidean topology. And
Sir,
how this topology on Z is generated. So this means this tau CF is proper subset of tau E, and uh, now the topology on Z is generated by this set. So what will be the basis? By definition, it is just you take tau cofinite topology with tau cofinite topology. This is the basis, right, for the product topology. And these all these elements are contained in the Euclidean topology. So clearly, the topology on Z is coarser than the topology on X. Okay, so this part is very clear because all these basis elements are itself in the Euclidean topology on R2. So this topology is smaller than the Euclidean topology on R2. But why it is strictly smaller?
sir,
Yes.
sir, take a product of two open intervals
Okay.
which are open in the Euclidean but are not open in that.
Yeah, exactly. So you just take open interval 0, 1 cross 0, 1. This is open in X but not in Z. So it has to be strictly quadsar. So your option is option C. So I hope you have understood this solution. So do you have any doubts? Okay, fine. Then let's move on. So let's see how the closed sets and those derived sets looks like in case of product spaces. So let x comma tau and y comma tau prime be two topological spaces. Also let a subset of x and b subset of y. Then show that the first thing is, then you just, we are taking the product topology in x cross y. Maybe, okay, let's mention this. Okay, so consider x cross y with the product topology. So here product and box topology both are same because we have only two topological spaces. Then show that the first option is if you take a cross b and if you take the closure means closure in the product space, then that is exactly equals to closure of a cross closure of b. And the second thing is okay, maybe let's start with the interior first. If you take the product and if you take the interior, then that will be product of the individual interiors. And the second one is the product of individual closures. But if you take the set of all limit points, then we have something different. So if you take A cross B and if you take the derived set, then it will be your A dash cross B bar union A bar cross B dash. Option D, okay, part D is about the boundary. So if you want to see the boundary of the product, then also the result is little bit different. So it is boundary of A cross B dash union A dash cross boundary of B. Okay, so the statements are very simple. So maybe let's try to prove this one by one. These are not difficult at all.
Sir, for boundary it is B dash or B closure.
No, it's closer.
Okay.
Yeah. Okay, so let's try to prove this interior one. So first thing, just before proving all these things, maybe note that the product topology on X cross Y is generated by the basis, let's say B, and it will be just G1 cross G2, where G1 is in tau and G2 is in tau prime. Okay, so this will be your basis for the product topology. So we need this thing. Okay, let's prove the first one. So we have to prove equality. So we have to prove two inclusions. So among them, one inclusion is very trivial. So can you see which one is easy?
Sir, A cross B interior is subset of A interior cross B interior.
So you are saying this one. Why?
Sir, because sir, A interior cross B interior is subset of A cross B interior.
Okay. And what will be the reason?
Sir, because A interior is subset of A and B interior is subset of B. So A
Okay.
interior
So
cross.
you are right. So A interior is subset of A and B interior is subset of B. So this will imply A interior cross B interior is subset of A cross B. And this is two product of open sets. So this is an element of the basis. Means it is itself an open set. So this will imply A naught cross B naught is subset of A cross B whole naught. Because this is the largest open set contained in the product and this is a open set. Okay, so one side is very easy. Now we want to prove the other inclusion. So we want to show this one. So how to prove this? So let's take an element from the left hand side. So let x comma y belongs to interior of A cross B. Then what is the definition of this? So this means x comma y is an interior point. So this will imply there exists an open set G such that x comma y belongs to G and this is subset of A cross B. Right? This is the definition of interior point. But G is a open set in the product topology. So it is union of members of this basis. So X must be contained in an open set of this type. So this implies there exists G1 belongs to tau and G2 belongs to tau prime such that this point x comma y is in G1 cross G2. This is subset of G and this is subset of A cross B. Okay. But from this what can we conclude? So this will imply X belongs to G1 which is subset of A and Y belongs to G2 which is subset of B. So from this what can you say? So that means X is an interior point of A and Y is an interior point of B. And that implies X comma Y is a point of A naught comma B naught. Okay. So we started with a point in the left hand side and that element belongs to the right hand side. So we have this inequality. So this implies the interior of the product is product of the interiors. So if you use this result, then in the previous problem you can easily compute this interior of the set in Z. If you cannot directly see that why it is not an open set in Z, just use this result. Okay, so this proves the first one. Okay, so maybe let's go for the second one. So we need to prove that the closure of the product is product of the closures. So again, one direction is very easy. So which one is easier?
Sir, A cross B closure is subset of A closure cross B closure.
Yes, exactly. So A subset of A bar and B subset of B bar. So that will imply A cross B is subset of A closure cross B closure. And this one is a closed set. Can you see why this is a closed set?
Sir, because A closure is closed in X and B closure is closed in Y.
So does that mean the individual product is closed?
Yes, sir.
So you need to prove that the complement of this set is open. So this is a closed set in the product topology. So what will be the complement of this set? So what will be the complement of this set?
The product of individual complements.
No, that is not true. That is not true. So it will be much more bigger than that. So it will be actually, you have to take the complement of the first thing, and you take product with the other set, then you take union, and you take the first set and you product it with the complement of the other one. Okay, so this is just set theory. This is true for any general case. So this is just set theory. You just try to prove it. Like you need to prove both side inclusions. You pick an element from the LHS and prove it belongs to the right hand side, and do the other way. So it is not just difficult. You just try to do it by your own. But try to remember this. So this is a closed set. But closure of this product is the smallest closed set containing A cross B. So this closure will be subset of A bar cross B bar. Okay, now we have to prove the other inclusion. So now we want to show A bar cross B bar is subset of A cross B bar. Yeah, do you have any idea how to prove this? Okay, let's try to prove by element wise. So let's take an element from the left hand side. Uh, let's take x comma y from A bar cross B bar, and this will imply x belongs to A bar and y belongs to B bar. But what we want to prove is x comma y belongs to A cross B bar. So what is the definition of this thing? When an element belongs to closure of some set, so this will be true if and only if every open set, okay, so for every open set G which contains this point x comma y, intersection of G with A cross B should be non-empty. That means this point has to be an adherent point, right? So this we have to show. So let G be an open set in x cross y such that x comma y belongs to G. So we have to prove intersection of G with A cross B is non-empty. But if we use the basis of the product, this thing, then what we will get? So this will imply there exists some G1 belongs to tau and some G2 belongs to tau prime such that this x comma y is in G1 cross G2 and this is subset of G. So now we will use this point. So this will imply G1 intersection A is non-empty and G2 intersection B is non-empty, right? So for the first one is true because uh, X belongs to A closure, and this one is true because Y belongs to B closure. So what can you say from this? So this will imply G1 cross G2 intersection with A cross B should be non-empty, right? But this will imply, so your G1 cross G2 with intersection A cross B, this is a non-empty set, but this is subset of G intersection A cross B. So this is also non-empty. So the smaller set is non-empty, means the bigger set is also non-empty. So your x comma y is an adherent point. So we have taken a point from the left hand side and we have proved it belongs to the right hand side. So this completes this proof. So is it okay? Yeah.
Sir, G1 cross G2 intersection A cross B is non-empty.
Yes.
Is there any set theory result
So what
using
will be
G1
this
intersection?
intersection? This intersection is G1 intersection A cross G2 intersection B.
Okay, sir.
Yeah, this is just set theory. Yeah, any other doubts or queries or comments? Okay. Okay, then let's move on. So maybe I want to do some other problem. So maybe I can skip at least one. So you try to prove this third one. I will do the fourth one. Okay. So this is also just set theory and the definition. You try to do the third one. Let's do the fourth one. The result related to the boundary. So what we want to prove is the boundary of A cross B is boundary of A cross B bar union A bar cross boundary of B. So this we want to prove. So what is the definition of boundary?
Closure minus interior.
Yeah, closure minus interior. So boundary of A cross B is the, you take the closure of this set and you subtract the interior. So what is this? Subtraction means you take A cross B and you intersection with the complement. Sorry, X cross Y. Okay, maybe let's keep this for now. But for closure and interior, we have the result, right? So what we can write is, it is just A bar cross B bar, and you subtract A naught cross B naught. So what is this difference now? So this is just A bar cross B bar. So what is the usual subtraction? This is just intersection with the complement, right? So complement means you take the whole set. Am I correct or what? A naught cross B naught. But what is this complement that we have already seen little bit ago?
X minus A interior cross
Yes. So let's write
Y.
this. So you first take the complement of the first one and take the product with the other set, means the other whole set, and you take the first set and you take the complement of the second set. So from this, what can you say? So this is just let's
Interior with first one union, interior with second one. So intersection. Sorry.
so let's
Inter-
distribute this intersection. So A bar cross B bar intersection with the x minus A naught cross Y. This thing union A bar cross B bar intersect with x cross Y minus B naught. Okay, so we have just distributed the intersection. But what will be the first one? So intersection of two products is the individual intersection that we have seen right now. Means I have just mentioned. So this is A bar intersection x minus A naught. This product with B bar cross B bar intersection Y, and union with similar type of result. So A bar intersection X cross B bar intersection Y minus B naught. Okay, I think up to this clear. But can you see what will be this set?
Boundary of it.
Yeah, it's just the definition. So this is just boundary of, and if you, and what will be this intersection? This is just B bar, right? The smaller set. So this is del A cross B bar. Now the second part. So A bar intersection X. This is just the smaller set A bar. And this part is just the boundary of B. So this gives the required result. This is the exactly what we wanted to prove. So is it okay? So here we are using a lots of set theory. You just need to do that part. If you want to verify that thing, you just try to prove this line by line. This is not difficult. So this completes the proof. So do you have any doubts? So I have done 3, A, B and D. You try to do the third one. Okay, so you have to prove it element wise. That much I can say now. You try to do it using the definition. Okay, so one small application of this that will be easier. Let's see. So true or false. So again, let x and y be two topological spaces. I am not mentioning the topology because that I don't need. Also let a subset of x and b subset of y. Now suppose a is densed in x and b is densed in y. Then the product will be densed in the product. Okay, so you have two topological spaces. One is x, other one is y. Here you have a subset of the first one. Here you have a subset of the other one.
True.
Sorry.
So the statement is true.
Okay, so why?
Sir, because closure of A cross B is equal to closure of A cross closure of B.
Yes,
Since A
exactly.
and B are dense, so A closure is X and B closure is Y. So A cross B closure is X cross Y.
Yes,
Hence,
exactly. You are correct. So A is densed in X means A closure is X by definition. B is densed in Y means B closure is Y. So this will imply the closure of A cross B is basically the product of the individual closures, and that is X cross Y. So A cross B is densed in X cross Y. So this is very easy if you use the previous result. Okay. Okay, I hope this one is clear. Okay, so problem number 5, I think. Yes. So again, I will use the same assumption. So I'll just copy this part. So again, we have two topological spaces. No, it is not copying. Yes. So we have two topological spaces, X and Y, and A is subset of X and B is subset of Y. So give, okay, not this. Okay. Give examples of sets A subset of X and B subset of Y such that the following need not hold. Okay, and what are the cases? The first one is A dash cross B dash is A cross B whole dash. And the second one is the product of the boundaries is same as the boundary of the whole product. So these two things may not hold. For that we need to give example. Okay. So this one is the product of derived sets, and this is the derived set of the product. So for the first one, do you have any example?
Sir, you can take whole set.
Sorry,
It's trivial. Sir,
sorry.
A is equal to X, B is equal to Y.
Okay. Then
Then it will hold.
what are the topology in your sets?
Any topology.
Is it true? So if you take discrete topology, then it will be equal.
No, I am saying that take A is equal to X and B is equal to Y.
Okay.
Then X interior cross Y interior is X cross Y.
So which one you are saying?
Sandeep, before you have to define some topology, maybe standard topology. Like that, you have to
Whatever
define.
topology you take, this will always hold.
Means sir is saying, give me such an example which will not hold.
Yeah, you need to give an example of topological
Okay.
spaces.
Sorry, sir. Sorry. Following need not hold. Okay. Sorry.
Yeah, okay. Yeah, this not, I think I should maybe. Yeah, this need not hold, right? Because in the previous thing, what we have proved is something different. So that's why I'm asking for these examples. Okay, maybe I will write. Okay, do you have any message or not? Okay, so let's take your x as well as y is r. Okay, I should write it in blue. So both your sets are R, and you take it with the usual topology. Okay. Now what you can do is just both A and B is your open interval 0, 1. Then what can you say about both these sets? Can you compute? So what is your A dash? What are the limit points?
Close 0, 1.
Okay. And what is B dash? That is also close 0, 1. Here. So what is A cross B is
This is also, sir.
okay. In Euclidean case it will be 2. So let's not take this one.
Sir, what if you take one side closed and one side open?
No, I'm saying if you take A as this and B just as this finite set, then what will be your A dash? It is close interval 0, 1, but B dash is empty. But what is your A cross B? So it will be this line and this line. No,
Line
this will
segment.
not. No, in Euclidean case it will not work. Sorry, this is my bad. So maybe you need to take some other topology.
Sir, cross product will be, sir, empty, na? If
So
one set is empty, then other will be also empty.
sorry,
Sir,
but
if you
A
take,
cross B dash, that will also be empty in that case. I think in the Euclidean topology it will
no,
not work.
sir, how, sir, if you find the limit points of a line segment in product topology, then that will be the whole line segment,
So
na?
here your x cross y is R2 and
Yes,
your
sir.
topology is the product of the usual topology, but in this case it will be the Euclidean topology on R2 that we have already seen in the lectures.
Yes, sir.
So here the
Then
basic open sets are disks, right? Disk you can take, or you can take squares or rectangles. That those are the basic open sets.
so the sir, so limit points of a line segment in this case will be the line segment, na?
No, those
Oh,
line segments as empty derived set, right? Because if you take a line segment, it cannot contain a disk, right?
you are, sir. We are talking about limit point, na, sir.
Yes,
Limit point
yes.
means that open set should intersect at least at the other point other than
Yes,
that
yes. Sorry. I made some mistake. Yes, you are right. So
that
let's try this again. What our sets are real numbers with the usual topology, and A is the open interval 0, 1 and B is 0, 1. So A dash is clearly 0, 1 close interval and B dash is empty. But what is A cross B? This is just 0, 1 cross singleton 0 union 0, 1 cross singleton 1. And what will be the derived set of this? Can you say what will be the derived set of this if you use the previous formula? So let's compute the derived set of this one using the previous formula. So open interval 0, 1 cross
sir, I think
singleton.
sir close 0 1 cross singleton 0 union close 0 1 cross singleton 1. We can see it by figure from figure, sir.
Yes. So okay, maybe let's use the formula in the previous question. Okay, that will also help. So this one, you take the derived set and you product with the closure and you do the other way. Okay, so for the first one, the closure is just 0, 1 cross 0 and union. The derived set is again 0, 1 cross 0. So it will be just this set itself. So this will be close interval 0, 1 cross 0 union close interval 0, 1 cross 1. So this is basically close interval 0, 1 cross 0, 1, and this is non-empty. But your A dash cross B dash is empty set. So this will give you a counter example. Yeah, thanks. It was just out of my mind. So yeah, I hope this one is okay. And I think this same example will work for the boundary also. You just have to compute the boundary and you do it using the formula in the previous page. Okay, so try the same example for the second one and let me know if it is working or not. Sample for this also. Okay. Okay, so I want to do some other things also. So far, do you have any questions? So far we have not done any question on infinite box or product topology. Maybe let's do at least one. Okay, so for each n, each natural number n, let xn is the set of all real numbers with the usual topology tau e. Now consider the infinite Cartesian product. So we are taking product of R with itself over the whole natural numbers. And for this we have some notation. Some books use this. This is R power omega, like that. Okay. So we have two questions. Maybe here the first one. Consider R power omega with the product topology. So this is the infinite product. Then which of the following sets are open? Okay, so the first one is product of un, where n belongs to natural numbers. But what is un? Un is just this interval for each natural number n. What is b? Again, it is product of this un, but un here is so sine inverse n by 2026, comma sine inverse n by 2026. And this is also for all natural numbers. And what is c? Again, we will take product of this un, where un is open interval minus 1 comma 1 for n equals to 1 to 26, and it is the whole set R for n bigger than 2026. Okay, maybe let's do this one first, then I will go to the box topology with some other things. Okay, so here our set is R omega, means product of R with itself, where the product is running over the natural numbers, means the index set is the natural numbers. And each xn is equipped with the usual topology, and we are taking the product topology. Then we have three sets. We need to check which are open and which are not. So what about the first one? Product of open interval minus 1 comma n to 1 comma n. Sorry, 1 by n, minus 1 by n to 1 by n. Is this open in the product topology?
No, sir.
Uh, can you say why?
Sir, because in product topology, open sets are those where finite sets are open and rest are, sir, the whole set in product.
Yes, exactly. So this is not open. because if this is open, then this has to be the union of the basis elements. But basis elements, you have only finitely many components. In finitely many components, you have proper subsets. But in this case, in every component, you have proper subset. So A is not open. So the main reason is this because this set cannot be written as union of the basis elements. Okay, so that is the main reason. So I have not written the whole thing, but that is clear. But what about the option B?
So then only the option C would be in open set because option C will
Sorry,
be
your
with
voice
R.
is very low.
So then only option C would be an open set. D will
Why
not be an
option B
open
is
set
not an open set?
because D will never be, UN will never be equal to R for some number. Because every single UN is a finite,
Is it so?
finitely and inverse is sign inverse of n to n what a real number, set of real numbers.
What is the question, sir?
So what about the option B? Option C is an open set because that is a basis element. But what about option B?
Same goes with sir option B.
It is not an open set?
Yes, sir.
Yes. So it is not an open set because on all the sets, not all the sets, only there are infinitely many sets which are proper subset. So maybe I will just write it in common thing. And option C, it is open because it is itself a basis element. Okay. Okay, maybe now let's move to the box topology. Okay, now consider two.
Sir, what is the reason given for B?
So what will be these sets? This set can be whole R. When this set will be whole R?
So for n natural numbers, it won't be R.
For N?
N belongs to n,
Yes.
so it will not be R.
It will not be R. Right. So it will be whole R only when N equals to 2026. Am I right or what? No. No, sorry. It will never be the whole set R. Right?
Because it's codomain. So domain is sir minus pi by 2 pi by 2.
Yes, exactly. Uh, it's codomain. So UN cannot be the whole R or infinitely many, or basically the same reason. This cannot be written as union of basis elements. So you
Sir,
just
it
need
is always sir it is always a subset of closed minus 1 1.
Yes.
Sir, even though if I give n equal to 2026, it will be pi by 2 comma pi by 2,
Yes, exactly. So I'm
which is
saying
which is empty set. Open interval pi by 2 to comma pi by 2.
sorry, this thing should be minus. Yeah, okay. So UN is always a proper subset of minus 1 to 1 for B. Okay. So now the reason is very clear. Now it is okay. Is it okay now?
Sir,
Uh, sorry, do you have any doubt? Uh,
Your
actually, your
voice is not clear.
I'm not able to hear you properly. Can you be little bit louder? Okay. Okay, now let's move on to the next problem. Now consider R power omega with the box topology. Then which of the following sets are open? Okay, so the maybe the same things for first two options I will take same.
Sir,
Yes,
box topology is always finer than, in case of infinite set, always finer than product topology.
yes,
Is this true?
yes, exactly. It is true. It was done in the lectures also. You can go back and take a look. And option C is okay. Let's do only these two because the other thing is very trivial. So what about these two? Which one is open in the box topology? Yes.
No one, sir.
Uh, option A, it is open because it is product of open sets, so it is an basis element. It is
Sir,
open.
infinite product will, sir, lead to, sir. Uh,
It
sir,
will
when we
lead
take limit, sir, n tends to infinity, what we will get?
n tends to infinity. Why you are taking that? I don't know. So what is the
Because
definition? It is just product of open sets, and for any natural number n, this is an open set because minus 1 comma n to 1 comma n is open for all natural number n. So this product is a basis element of the box topology.
yes, sir, correct.
So it is a basis element. But what about the second one?
It will not, sir. For n is equal to 2026, it will come out to be minus one closed interval.
Yes. So you will get one closed set. because I will just write the same thing, because it cannot be written as union of basis elements. Because if you see, uh, what is your set? So for n equals, here you have u1 plus dot say some here somewhere at u26 and so on, and this one is close interval -1 to 1. So if this your whole set, if this one is open, then this is union of basis elements. So at this position is also union of open sets of R, but this one cannot be written as union of open sets of R, right? So this cannot be an open set. Now, is it okay for you? Did you get the point? Okay, I don't have much time, so maybe